Okay, so let's start our lecture today. So, sorry, last time it was powered out during my lecture. So, there's some part of my lecture that's not being recorded. So, but the idea is that you want to show that the derivative of this difference is equal to 0. What we do is that we compute the difference of this period difference, and then so because the period difference is simply just the, so here, so this is like the expansion of the z plus omega 1, which is this guy, and then minus, so this is just zeta z, right? So it's start with 1 over z and then minus, sorry, this whole thing is negative zeta z, okay? And then so what happened is that if you take the difference between these two, so here I find the common denominator, right? So if you find the common denominator of this z and z plus omega 1, so it's their product, and then I just find the common, and then I do the cross multiplication on the numerator, and then I do the subtract on the numerator. So that gives me the sum of these two fractions. And then we also know that by this property, right? So this is a limit. Let's say this is one limit and this is another limit. And then so their difference is just the limit of their differences. Okay? So and then finally what we do is that, so for here, right? So this one, the z is being cancelled out. So what's left is just the omega 1. And then for this part, so what's left is just the so here basically we cancel this term 1 over omega, and then for this term, right? So here it has z minus omega 1 over omega squared. So here this has z over omega squared. So what's left is just the negative omega 1 over omega squared. So which is this part. Which is this part, sorry, which is this part. And then this part corresponds to, you take the product of this, sorry, you take the sum, you take the difference of these two fractions, then you get that. Okay. So and then after you manipulate with the numerator, so what we get is that you will I will just get omega 1 on the numerator for this guy. Okay. So this is just the difference of the period. This is just the difference of the period term, the periodic difference. Yeah, this is just the periodic difference. And then so now what I want to show is that either this term is a constant, or I take the derivative, it will give me 0, right? So I have to think of why. If I take the derivative of this guy, so basically, essentially speaking, so y, this is just a constant term, yeah. So y for any z, right? So the whole thing will give you the same. I think the reason might be that because okay, so here we go. So when we are trying to take the derivative, right? So we know that so this one basically can be realized as the this function plus the limit of the partial sums, right? So so this is just a it can be viewed as the limit of a limit of a the limit of a sequence of holomorphic functions that's being converging on compact subset of C minus the wedge, C minus the C minus the at this point, right? So, so basically we know that if we so this function is a limit of sequence of the holomorphic function, right? And again, like converges. It has a converges uniformly on compact subset of the C minus wedge. Okay. And also I think it's minus a wedge and also wedge using the origin, because the origin must also be excluded. Okay. And then so this is the limit function of this guy. Roughly speaking, it's the limited function of this guy. So basically, if you take the derivative of the limit function, so the derivative of the limit function must be equal to the limit of the derivative of the partial sums. Yes. So it must be the limit of the derivative of the limit function is equal to the limit of the derivatives. Yeah. The derivative of the limit function is equal to the limit of the limit of the derivatives. So here, so this one, so basically if I take the derivative of this guy, right? So here basically when we take the derivative of this guy, so and then we take the limit, right? So this is exactly the limit of the derivative, and then this is just the derivative of the limit function. Okay, so yeah, so again we use this property. Okay, so we use this property, and then what we get is that so here this so for the bottom term, so this is just basically the the chain rule, right? So this is just the chain rule. Okay. And then chain rule and the product rule. Okay. So and then so what happened here is that this is also chain rule plus the product rule. Okay. So and then after some like, because here there are some z's and the omega 1, so after I collect the z term and then the omega 1 term, and then so this is just the, and then for the limit, so this is the limit terms that we are, yeah, so this is the limit terms, and then we also collect the z terms, and then this minus 2 omega and then plus omega 1, and then this is just the after taking the derivative, right? So the bottom, because the power is this is to hosting to the -1 power, so you after applying the chain rule, yeah, so then it becomes that. Okay, so so basically so we have this as our summand. Okay, so and then so one thing that we can notice is that so there are some patterns between this and that, because so basically, so this is sum over all the omega not equal to 0 of this z plus omega 1 minus omega, and this is, and then squared, and then times z minus omega squared. Okay, so if we just look at the denominator here, you see that if so here there's an extra omega, right, compared to this one, right? So here, and then we are summing over all the omega not equal to 0. So basically, this is a term that corresponds to where omega is equal to 0. Yeah. So this corresponds to a term where omega equal to 0. So here I basically I just say that basically we just sum over all the omegas. Okay. So of the same thing. Okay, and same thing on the numerator, right? So when this this is just the omega equal to 0 scenario of this numerator. Yeah. So basically, this term is the omega equal to 0 scenario of the summand here. So basically, when I add this up into the sum, then it just sum over all the omega. So the question is that, so why does this one give you 0, right? Mm, let me think. So why I give you 0? Uh, uh, so why I give you 0? Because so why I give you 0? Oh, why? So what is this sum, right? So maybe let's think of the question. What is this sum? Uh, um, mm, okay. Uh, uh, yeah. So why? Okay. So maybe I think um, I'm running a little bit into trouble, running into trouble here. So yeah, I'm running a little bit. So okay. Shoot. Okay. So uh, uh, okay, so maybe let's write out. So so uh, um, okay, so maybe I need to look for some help here. Okay, so yeah, so I'm opening my notes. Okay, here. Good. Yeah, so I'm speaking to the microphone. So, oh, so yeah. So here I'm basically I'm on trouble with showing the y stress. The zeta function, it has period omega 1, right? So basically I know the definition of the zeta function, and then basically I want to show that the zeta of z plus omega 1 minus zeta z is a constant, right? So what I do is that I compute what is the zeta of z plus omega 1, and then I just compute what is zeta z, and then I do the subtraction. So I want to do the subtraction. I get negative omega 1 over z times z plus omega 1 plus the sum over of the omega not equal to 0 of negative omega 1 over z plus omega 1 minus omega times z minus omega 1 over omega squared. So when I take the difference of this guy, so what I have is that I'm having the difference is equal to the the derivative of the limit function is equal to positive omega 1 times 2z plus omega 1 over z squared plus z plus omega 1 squared, and then plus sum over all the omega not equal to 0 of omega 1 times 2z minus omega plus omega 1 over z plus omega 1 minus omega squared, whole thing squared, times z minus omega squared. Okay, so knowing that the first term is just the second sum where the omega is equal to 0, so basically I can combine them into the sum of omega over all the omegas including 0 of this summand. Okay, so now however I'm pretty sure that the derivative of this period difference term must be equal to 0, but it is not obvious for me to see that from what I get as the summand. So can you help me with that? Oh shoot. Yeah, so can you help me with that? Okay, so yeah, so yeah, so if we just look at the difference term, right? So let's simply plug in z equal to 0 and see what we get. Yeah, so let's focus on the case where z equal to 0. So z equal to 0, what we get is that this ddz at z equal to 0 of the difference is equal to the sum over all the omega of in this wedge union the zeros. Okay, so so this is the lattice point, right? So this is the this is the lattice point. N1 omega 1 plus N2 omega 2, where N1 N2 is all the integer tuples, excluding the 0, 0. Yeah. So it is union. So I will union like 0, 0. Okay. So I'm adding the 0, 0 back to this wedge. And then, so what I do is that, so for summand, what I have is that, so this is omega 1 times negative 2 omega plus omega 1. And then over, so this is omega 1 minus omega squared, negative omega squared. Hold on. Yeah, so it seems that we are getting the same thing, right? Oh, yes, I think, yeah. So, wait. Okay. So what do I think? So wait. Okay. I think. Yeah, I think we are. So. Yeah, so this is equal to, maybe this is a special case. Okay, I'm not so sure. So, in this wedge union this 0, 0, right? And then so this is just negative 2 omega minus, oh sorry, plus. No, not that, not this one. So why this is true? So what does that equal to? Okay, so I'm under thinking that so basically for this term, right? So maybe I can just yeah. So maybe what I can do is that so this z plus omega 1. So yeah, I'm not so sure. I'm not so sure. I was thinking about maybe after some reorder, right? So maybe maybe this z plus omega can be it could be hit by another rearrangement. Yeah, so I'm thinking that, but yeah, I don't think what I'm thinking is correct. So uh, let me see what happening here. Um, oh, okay. Sorry, I think I made a mistake here. So this should be a plus. Okay. Okay. Oh, okay. Okay, so um, okay, so I think I'm thinking in the wrong direction. So I think what happening is that um, so so this derivative, right? So I shouldn't I shouldn't um, uh, bring the difference term altogether. So what I want to do is that I want to just focus on the relation between the y zeta function and the p function, right? So this is what I want to do. Okay. So basically, so what I have is that, so 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 this is equal to so this is equal to exactly negative the p prime of z plus omega 1, right? Plus p prime of z. Okay. Oh, sorry, not p prime, but just p, right? Okay. And then, so what does that equal to? So, okay, so I know that this p has period omega 1, right? Yeah, so we show that p, yeah, so we show that, p of z plus omega 1 is equal to pz. Yeah, so I see. So wait. So so why this is really true? Let me quickly recall. Oh. Yeah, so yeah, so we showed before that this pz is periodic. So basically yeah, so I showed before because namely because you take this as, so you take the pz as so basically you take the pz as 1 over z squared plus sum of omega not equal to 0 of 1 over z minus omega squared minus 1 over omega squared, right? So what we do is that we take the derivative of this guy, right? So so the derivative, so basically the p prime z is equal to negative 2 over z cubed plus the sum of over omega not equal to 0 of sorry, this is sorry, this should be minus, right? And then 2 over z minus omega cubed. Right. And then, so what happened is that okay. Oh. So it's equal to negative 2 times sum over all the omega over of 1 over z minus omega cubed. Okay. Okay. And we show that this guy is doubly periodic, right? Yes, because though this one is doubly periodic because okay. So yeah, sorry, maybe I want to pause here. So yeah, what I want to say basically is that yeah, so basically this argument, right? So basically, what I want is that I want to show that. So here I want to show what I want to show is that so P prime Z is doubly periodic, right? Okay, so so basically, if you replace Z by yeah, so if you replace Z by Z plus omega, then it's gonna be the same limit after you do some reordering, right? so if we yes, I think so. Uh, mm, if we replace z by z plus omega 1, then we will have the same limit after reordering. After reordering. Okay. Okay, so however, the thing is that, okay, so the thing is that, so here our aim, okay, so we want to show that okay, so however, the question is that, so this reorder can only happen when the series is absolutely summable, right? So so let's see. So why if you have yeah. Oh, okay. Yes. So this is converging for sure. So so because because we know that the sum of the omega cube converges, right? So yeah, I think it could be done using a okay, so I'll try to start with here next time. Okay. Okay. Yeah. So Yeah, I think maybe there is something that not so clear when I was trying to show this as the first time. So yeah, so let me just show this next time, okay? And then after I show this, then after replace z by z plus omega 1, then we will get the same yeah, so we will get the same limit after reordering. Wait. I should show p prime z equal to 0, right? So if z equal to 0, p prime z, what is p prime z though? Okay. Okay. Anyway. So, I show that this p is periodic. So this is equal to 0. Okay. So, yeah. So basically we're done. Okay. Okay. Yeah. So yeah. So I'll just conclude from that. I'll just start with yeah. I'll start with yeah. I'll start with yeah. I'll continue next time. Okay.